Welcome back. In this video, we're going to discuss the second part of our shaft consideration, which is having to do with deflection and vibration, basically how much things are going to move around. So these are going to be our two main concerns, and they are going to be sort of the latter concerns because we need to know a lot of properties beforehand. So you recall deflection that you learned about in mechanics and materials, and vibration, hopefully you've learned about a little bit in MDC, because those are the two classes that we talk about these things. And these are important concerns for a shaft because while there may not be crack growth and there may not be fatigue failure or yielding, we can still experience deflection, which is going to cause the components of our that are on our shaft not to be located or not to be operating correctly. And if we hit a critical speed, we can actually induce vibrations into our system that can cause failure in other areas, that cause dynamic loads we may not be expecting. But in order to do deflection and vibration, we need to know several things. We need to know diameter, we need to know material properties, and so this is why we typically do this step afterwards, after we do the layout, material, and geometry selections. So obviously first we have to find whatever diameter that we want from our previous process. We're going to calculate the deflection and slopes that are of concern to us. Those deflections and slopes are going to be the issues that may come up. Once we know our static deflection from a constant load, we can figure out any vibration concerns. This is also called whirling, when our shaft begins to kind of rotate dramatically out of control, and we'll show a little video of that in a moment. And finally, of course, we have to iterate on all of our choices that we made before in the diameter and material in order to avoid that. So recall from way back when we were talking about in mechanics and materials that there's a relationship between the force that we put on something and how much it deflects. And the process of going from one to the other is part of why we studied beams so much, and it directly relates to what we're doing with shafts. So the amount of deflection, y, typically in a negative direction, is a function of basically how far along in the x direction we are from a shaft based on how it is loaded. And then the slope, of course, if we have some beam with some loading on it, the slope, of course, is going to be the derivative with respect to where we are. So the slope at any point in time of that beam. The bending moment, which is reflective of that sloped shape, is actually relatable to our material properties. So we can figure out that the second derivative with respect to x of that beam, whatever the final beam shape is, tells us our moment diagram. And oftentimes we've done this the opposite way. We move from forces to shear to bending moments, but we can of course work either direction with the lovely invention of calculus. So the shear moment diagram, of course, will be the third derivative with respect to x. That gives us your shear diagram. And our shear diagram is driven by whatever actual forces we have. So d4, fourth derivative, again with respect to x, and this is your force diagram. So typically when we've been talking about shear and bending moment diagrams, we've been drawing them this way. And as long as we know material properties and geometry, we can start figuring out slope and ultimately deflection. There are numerous ways to do beam deflection. If you have a preferred preference of one method or another, just do whatever. I'm going to link to and show through using an example with the superposition approach, where we simply use trying to find an existing similar scenario, because of course the example I have is intended to do that. All right, so when it comes to deflection, there are two concerns. One is, are we going to have too much deflection such that it interferes with our other components? So that is an important consideration in terms of if we've accounted for in the movement in the other components for the amount of deflection that we expect to see in our shafts. And again, this is why we want to keep a shaft short. The other side of that might be the slope. So for a particular element, such as a bearing or a gear, there's a certain amount of acceptable slope that can occur in that shaft. And those will be specified by the bearings. And again, there's a table in Chapter 7 that discusses typical values for different types of bearings and different types of gears. The other one is the amount of twist angle. So if you imagine gears are not infinitely thin, even though we've kind of pictured the forces as acting on there, if there's some torque acting on this shaft in the center, then there is some angle of twist here that is occurring, and so there's maximum angles of twist that are going to be unacceptable to us as well. So these are the three aspects of deflection, and recall that from mechanics of materials, that all of these things are additive, so we can do all of this piecewise, which is typically the process because, again, our shafts are typically stepped, meaning that we can figure out the deflection by parts, or the angle of twist by parts, or the slope by parts. And the amount of twist from one piece to another we can add, and the amount of deflection that we can add, and the amount of slope we can, the slope will be at a particular location. So those are our concerns in terms of deflection. Our other concern is in terms of vibration. So what happens is what's called the Rayleigh-Ritz approximation is what we're going to try to find of the first natural frequency. So as you rotate a shaft, as it has a higher and higher RPM, at some point it can get to a natural frequency, and when it hits, when that shaft and the loads that it's carrying reaches a natural frequency, it is going to experience excessive vibration. So for a little example, watch the RPM on the bottom of this and wait for the excessive vibration. There it is. You see about 400 RPM. There it is. 2000 RPM. And then every time we hit an integer multiple of that natural frequency, we hit the second natural frequency, the third natural frequency, and it will do those vibrations again. But those, when you hit that natural frequency, it causes that high excessive vibration that we saw before. I'll come back one more time. There it is. So those excessive vibrations put a lot of impact and force onto your bearings and everything else in your system. So we want to avoid those as much as possible. So what we do is we figure out what is an approximation of the first natural frequency. And to do that, we first come up with what is the max static deflection. And then this maximum static deflection will tell us our critical speed. So the critical speed at about the point when we're going to hit that first harmonic is approximately, this is the Rayleigh-Ritz approximation, 30 over pi times g, which is gravity in this case, the force, acceleration of gravity, and that maximum static deflection. So if we're talking in meters here, then our gravity, of course, is going to be 9.81 meters per second squared. So if you're in millimeters, use gravity force in millimeters. Obviously, stay consistent in your units. Also, typically when we talked about deflection, we said in a negative y direction. Obviously, you take the square root of the negative value, you start talking imaginary numbers, it gets a little complicated. So this is the magnitude deflection. So this is going to get you some critical speed, and typically what we want is something much less than that. So the maximum speed that we ever want our shafts to operate at, this is max speed here, is going to be fractional of that critical speed. So good design practice might be 25% of this critical speed. So you can check to make sure that you're nowhere near these harmonics, because again, oftentimes we run motors a little hot. We might go a little bit faster, so we want to leave plenty of room here. That's why the quarter of the critical speed. You can obviously fudge a little around that 26% or whatever, but try to avoid that critical speed as much as possible and avoid that induced vibration. All right, so what we've covered in shafts is basically the three main concerns. Is it going to fail due to static load or fatigue failure, crack growth over time? And to take care of that, we look at having the right material with the right strength properties, having the right reducing stress concentrations in the layout, which reduces bending moments and is as small as envelope as possible, and then finding a diameter that will satisfy those constraints to keep it from either yielding or growing cracks over time, which is fatigue failure. And then the other special part of shafts is that because we've got elements spinning at high speeds, they have this ability to both deflect and wobble, and so we want to make sure that whatever static deflection, even if it's well within the elastic region of our part, is not going to cause problems with other components on the system. That, of course, depends on what components they're talking about, as well as avoiding this whirling, wobbly behavior that happens when we get to the critical speed. So when you do calculate deflection, you may find that that critical speed is surprisingly lower than you might think. All right, that'll do it for this video. Until next time.